So before we get into the second law of thermodynamics, I want to discuss an important notion, which is the notion of heat capacity. Okay, so heat capacity is a very intuitive idea. It's essentially how much heat do you have to supply to a system for its temperature to increase by a certain amount. So, so we saw that there was an equation of state where the state variable temperature or state function temperature is related to P and V. So this was called the equation of state. So we can use the equation of state to express the energy in terms of, say, the temperature and the volume. So I'm just using U, I could have used E. So this is the internal energy. Now, if I take a differential of U, calculus tells me that, multivariate calculus tells me that there's du by, say, dt, but that has to be taken when V is constant, dt plus du by dv, t is constant, dv. If you think about it a little bit, you know, this guy is actually nothing but the gradient operator. So we can visualize, if you haven't done too much multivariate calculus, you know, we can visualize this in the following way. So you have some axes, which is the v axis, and you have another axis, say the t axis, and you have some, so this is the TV plane, television plane, and here you have some function, and this function is the internal energy function, okay? So what if you change the du in some random direction, if you go in the random direction in the VT plane, so you have a vector in the VT plane, you're going in the dt and the du direction. So this is your unit. Then how does the u function change? The u function changes in this way, right? Because is that clear? This is like a little bit like the gradient. Okay. So this is what it means to take the partial derivative for a multivariate variable. So if you haven't, like, I'm not going to use the technical language of calculus, I'm just going to use some intuitive pictures. Okay.
Sir, is that U on the z-axis?
Yes, that's u on the z-axis. Yes, that should be.
Right. Right. Thank you.
Right. So, right. So now what we can do is that, you know, well, from the first law, we know that the change in Q is d of u. Now I'm using u instead of e, okay? Plus p of d of v. Now, we just saw what d of u is. D of u is the partial derivative of u with respect to t with v constant dt plus the partial derivative of u with respect to v with t constant plus p and the whole thing multiplied by dv. Okay? And then, from here we can say dq by dt is du dt v plus du dv t plus p, and here it'll be dv by dt. Okay, so this is all very easy stuff. Now we can define two types of heat capacity. So heat capacity number one is the heat capacity when the volume is constant. That is, you change the temperature by a certain amount, but keeping the volume constant. How does that affect the absorption of heat? So that is defined. This is the definition. The definition of that is dq by dt v, right? And what we can see is that if we right. Du. Right. Yeah. So because the volume is being kept constant here, that means that in this equation, this guy is going to be 0, right? And therefore, we can say the heat capacity with volume constant is just going to be given by the first term here. So it'll be du of dt. Of course, in this case, this would be just a partial derivative. Okay, so this is the expression for the first heat capacity. Okay. The second heat capacity is the heat capacity where pressure is kept constant. And that, there is really no simplification there. The first term remains, and the second term also remains. The only thing that changes here is that now we can just think of it as a partial derivative. So these are the two heat capacities. And heat capacities are extensive quantities because the bigger your system is, the greater the heat capacity is going to be. So you can turn them into intensive quantities by, say, dividing by the mass of your system. Okay, so that's kind of trivial observation. Okay. Now, in discussing the second law, we are going to be using the ideal gas as an example. Okay, we are going to use that as our system. So let's review some aspects of the ideal gas.
Sir, I have a question.
Yes, please.
Sir, can you please scroll up a bit? In this CP, partial derivative of V with respect to t is
Right.
the operator ddt and just the difference of V divided by difference of t. Are these the same thing here?
Yeah, I mean, you mean that except here it's a partial derivative, so you are keeping p constant.
No, sir. I asked if the mathematical ddt operator and dv by dt, the change of volume divided by the change of temperature
Right.
in this after in the CP equation, are these
Yeah,
the same? The
they are the same.
operator.
Yeah,
Oh, thank you.
they are the same. Yeah. All right. So